This is a continuation of Chapter 7, and we just finished balancing equations. Now we're going to move into stoichiometry calculations. The first thing I want to review before we get into stoichiometry is what stoichiometry is, really. So we have up to now converted between grams of a substance to moles of a substance, and between molecules of a substance to moles of a substance, and but it's all been the same substance. And so what that's building towards is when you get to chemical reactions, okay, you have more than one substance. Oh, I need to change colors with that, don't I? There we go. So you have several substances in a chemical reaction. So once we get moles of one substance, we need to be able to correlate that to moles of all the other substances, okay? And so how we do that is with mole ratios. And the mole ratios are really simple. They're just taken from the coefficients in the balanced reaction. Now, it's really important to make sure that you have, in fact, balanced a reaction before you get a mole ratio. And so how we might read that, for example, is that 2 molecules of C8H18, octane, okay, or 2 moles. You can read that coefficient as molecules or moles, okay? 2 molecules of C8H18 react with 25 molecules of oxygen gas to give 16 molecules of CO2 and 18 molecules of water. And now any stoichiometry problems you're going to encounter will typically be with something like, if I start with 3 moles of C8H18, how many moles of oxygen do I need? Or how many moles of CO2 will be produced? And you're going to use the mole ratios to do that. Okay, as I said before, mole ratios are simply from the coefficients in the balanced reaction. And just pay attention to the question, the order of the substances, okay? So if I asked you, what is the mole ratio of C8H18 to CO2, just give those coefficients in the same order the question was stated. So the mole ratio of that would be 2 to 16. Okay, so pretty simple. Let's go ahead and do a calculation using mole ratio. Now, mole ratio is going to be used as a conversion factor, right? So conversion factors are always a ratio with 1 unit in the numerator and a different unit in the denominator, okay? And they just allow you to switch from one unit to another. And so if our given information, as always, we start with that, okay, in dimensional analysis. If the given information has units of moles of C8H18, then you want to place the mole ratio you're interested in. So the same units are in the denominator, so they cancel. So you want moles of C8H18 in the denominator and moles or whatever you're trying to get to in the numerator. So this question is asking how many moles of CO2 form, so you want to make sure that that's what's in your numerator. We're going to branch out now. So far, the last couple slides, what we have been talking about is this part of the mole map right here, where we have learned to go from moles of one substance, I'll just call it A, to moles of a different substance in a chemical reaction. And we have used mole ratio as our conversion factor to get from one substance to the other. And we're going to combine that knowledge with what we learned before that, which is simply converting between moles of a substance to mass of the substance, or moles of the substance to atoms or molecules of the substance. So we're going to kind of just combine everything we know. And this map might be helpful for you to refer back to or print out. In a more linear fashion, this is what we're going to be doing most commonly. Typically in a problem, you're going to be given the mass of some substance in the chemical reaction before you can do any calculations, you want to first always convert to moles of that substance, okay? And remember, that's just molar mass. Anytime you see grams or mass in a problem, your conversion factor is molar mass. Once you're in moles of that substance, you can use mole ratios, okay, to get to moles of a different substance, whichever one you want in that chemical reaction. And remember, to do that was using mole ratios as your conversion factor. And then, of course, once you're in the moles of the substance you're interested in, we know how to go back and forth between molecules or atoms using Avogadro's number or mass. And typically, the typical stoichiometry problem will have 3 calculations, okay? So each conversion factor represents a calculation. That's 1, 2, 3, okay? And if you look at this kind of linear representation of a typical stoichiometry calculation, each arrow represents a calculation. So 1, 2, 3, well, in this case, 4. Okay, so 3 or 4 calculations, multi-step calculations. Let's work an example out. Always the best way to learn in chemistry. All right, here is the chemical reaction. It's balanced. You always want to check to make sure it's balanced. And the given information, 25 grams of potassium chlorate. Now, you're going to have to freshen up on your naming and writing formulas, okay? Potassium chlorate is this, but I'm not going to be there in a test to tell you that. So you need to practice and get fresh on that. All right, so that's your given information. What are they asking for? They're asking for moles of O2. Okay, so I want to tell you ahead of time. I just want to kind of make a map for us, okay? So we're starting with grams of KClO3. And I know that the first step that I always need to do is go to moles of that substance. I can't compare substance to any other substance until it's in moles. All right, so once I have moles of that, I can use mole ratio, right, to go to any other substance in that reaction I want. And that'll get, and this is asking me for O2, so I'm going to use mole ratio to get to moles of O2. That'll be my second step. Actually, that's my last step, because this question is being nice. It's only asking us for moles of O2. It's not asking for grams or molecules of O2. Okay, so that should be a 2-step question. Alrighty. So looking on the mole map, how we would approach that is we are starting with grams. Doesn't matter if you take grams on the top or grams on the bottom, okay? Remember, every arrow represents a calculation. So we want to first convert to moles, right? And, oh, that does ask grams. I didn't see that. Ask for moles and grams. Sorry about that. And the second step is going to be using mole ratio, okay, to convert from moles of the potassium chlorate to oxygen. And then the third calculation is going to be, once we're in moles of oxygen, we're going to convert to grams of oxygen. Alrighty, and here's the actual work. Now, as always, you can do it in 3 separate steps, as I've done here, or if you want to save time and you're comfortable with it, do it in one long run-on calculation. So, as I said before, step 1 is converting from grams of KCl3 to moles of KCl3. And of course, we know that we always divide by the molar mass, right? This is the molar mass of KCl3. Once we have moles of KCl3, we're going to use a mole ratio, and that's just from the coefficients in the balanced reaction, to convert to moles of oxygen, because that's what the problem's asking for, is oxygen. That was the first question asked. The second question is how many grams of oxygen. And again, anytime you see grams, you're going to be using molar mass as your conversion factor. Now, I want you to pay real close attention here for a minute. Oxygen, okay? This is not oxygen atom. This is diatomic oxygen. This is a molecule. It's got 2 oxygens. So be careful. The molar mass has to be for 2 oxygen atoms too. Okay, so always watch that. Diatomic elements, you've got to account for that and their molar mass. All right, so here's the final answer, 9.99 grams. And now I want to show you real quick, if you want to do it all in one step, you could just do a run-on. It saves time. But some students don't like it, which is fine too. Now, again, you have to be careful when you're doing stoichiometry to not only have the units moles or grams, but also what the substance itself is so that you don't get confused. Let's see. So there's my mole rate. Okay. So you just kind of do something like this in one long run-out calculation instead of the separate steps either. Alrighty, here's one for you to try. And so I'm going to suggest you go ahead and turn off the video again and then come back here and I'll work it out for you. All right, so I did it in kind of one long calculation this time just to show you both ways. And so most of the time you're going to be going from grams of one substance to moles of that substance. Then using mole ratio to get to moles of whatever substance the question's asking you about. And then often from that to grams of the substance, okay? So remember, each arrow represents a calculation. So your most common problem is going to have 3 calculations. So I'm going to start with the given information, as always. Okay, 1 gram of glucose right here. And again, anytime you see grams, that means you need to look up or calculate the molar mass of that substance. The molar mass of glucose is 180. Once you have moles of the substance you started with, use your mole ratio to get to the other substance. This question is asking for about water. So I'm going to use my mole ratio to compare moles of glucose to moles of water, 1 to 6. And then the problem is asking for grams of water. So I've got to go one more step and convert the moles of water to grams of water using the molar mass of water. Now, just a quick reminder here, when you're using molar masses in a calculation, make sure you don't round them to whole numbers. You're going to lose some credit there, okay? So either record all of the digits in the periodic table for a molar mass or at a minimum 2 digits to the right of a decimal. So then we carry out this calculation. So 1 divided by the molar mass, 180. Okay, and then times the mole ratio, and then times the molar mass of water. And I get that makes how many sig figs do I need here, guys? Let's see. The beginning information had 3 sig figs, so I'm going to stick with that. 600 grams of water can be produced by 1 gram of glucose burning. That's it. Just practice is the best thing to do. All right, so now we get somewhat trickier. Limiting reactant. So this is stoichiometry on steroids, basically, okay? So you've got a chemical reaction, and most of the time, for reasons you'll probably learn in 12.12, you don't have exact stoichiometric equivalents of both reactants. You typically have an overload of one or an excess of one and a deficit of the other. There's some good reasons for that, though. So again, as you'll learn next semester in 12.12, if you add excess of one of the reactants, you can typically not only speed up the reaction, but obtain more product. So you want to, it turns out though that the reactant that's in deficit, or that is the limiting reactant, the one that's going to run out of first, is going to determine how much product you can make, right? Because as soon as you run out of the limiting reactant, the reaction stops, right? It can't keep on reacting and making product with only one reactant. So the limiting reactant is basically the weak link. It's going to determine everything. It's going to determine how much product you make. And so the amount of product that the limiting reactant is capable of making, if at all converted, is called theoretical yield. Okay. So those are two vocabulary words you need to be real comfortable with, okay? Here's using a chemical reaction instead of hot dogs, okay? So look at this balanced reaction, which represents the combustion of CH4. And when I say stoichiometric amounts, if I had exactly 1 molecule of methane and 2 molecules of oxygen, I could get, my theoretical yield would be exactly 1 molecule of carbon dioxide and 2 molecules of water, right? But what if I skew the amounts I start with so I'm not using stoichiometric amounts? In other words, I have an excess of one and the other is a limiting reactant. So you need to be able to determine which one is excess and which one is limiting, because again, it's the limiting one that's going to determine how much product you can make. So this is simple math. Hopefully you can do this with mental math. So if I have 5 methane, so if I put a 5 in front of that, how many oxygens do I need? Well, remember to look at the mole ratio, right? So if I start with 5 moles or 5 molecules of CH4, how many moles of oxygen do I need? The mole ratio will tell you that, right? So look at the balanced reaction. For every 1 mole of CH4 that I use, I need 2 moles of oxygen, right? So that means if I start with 5 moles of methane, I need 10 moles of oxygen, right? I don't have 10, I only have 8. So that tells you that oxygen is the limiting reactant. Now this one is pretty easy to just do using mole ratios. That won't be the case as we get to more complicated problems. So I'm going to give you a method that works 100% of the time. It's pretty tedious, but it's very, very reliable, okay? And what it is down at the bottom here. You are going to calculate the amount of product, doesn't matter which product as long as it's the same one for both of them, the amount of product that could be made for each of the given quantities of the reactant. And you will find that the excess reactant will be capable, clearly, of making more product than the limiting reactant. Look at that a little bit closer. All right, so for example, if I start with 5 moles or molecules of CH4, and I want to know how much product I can make, I'm just going to pick a product. Doesn't matter again, as long as it's the same one you use for the other reactant. And so I'm going to now use the mole ratio to figure out how many moles of product I can make from this 5CH4. And it turns out I can make 5, so remember that number. I can make 5 product molecules, 5 CO2, right? So now I'm going to go and see how much CO2 that 8 moles of oxygen can make. And I'm going to compare. Okay? So I'm going to do the same thing starting with oxygen. If I have 8 moles of oxygen, how much CO2 can I make? Well, mole ratio again between oxygen. Okay, 2 oxygen makes 1 CO2. And it turns out I can only make 4 moles of carbon dioxide from this amount of oxygen. Do you remember on the last slide, it said that I could make 5 moles of CO2 from the CH4 that I started with? Okay, the 5 moles of CH4. All right, so here's the important part. The reactant that makes the least amount of product is the limiting reactant. Okay? The reactant that makes the least amount of product is the limiting reactant. And that's how you are going to identify limiting reactant 99% of the time. You've got to do a quick stoichiometry to product for each of the reactants, decide which one makes the least amount. Now, I want to point out something really, really, really important. So if you're kind of spacing out at me, pay attention. Okay, this is very important because it's a trick. It's a common trick on standardized exams for you. What if you weren't thinking or you had test anxiety, right? And you were just given these two and it said, which one's the limiting reactant? CH4 or oxygen? It has nothing to do with comparing the amounts of each you start with in grams, okay? Or moles, whatever. Notice that we have less of the CH4 than we do of the oxygen, but oxygen's a limiting reactant, right? So it has nothing to do with the overall quantity of the starting reactants, because you have mole ratios and molar masses and all sorts of stoichiometry there that's going to affect how much of each of them you need. So don't get fooled into this by just saying, well, this number's smaller, it's got to be limited. No, that's not the case. You have to go through the stoichiometry that I just described here. All right, here's one for you to try. This is a really important one, okay? Because it practices everything we've learned so far in moles and stoichiometry, okay? You're going to do all the calculations from grams to moles, mole ratios, and you're going to determine limiting reactant. You're going to determine theoretical yield, okay? So take your time, go back a couple slides if you need to, and that's going to be so important for your learning rather than just watching me do it. That's not going to teach you a whole lot. Just a couple other tips here. How do you know that you're dealing with a limiting reactant problem and not just a regular stoichiometry problem? Whenever you're given quantities of both reactants, so see, this tells me I have 100 grams of nitrogen and 50 grams of hydrogen. If you're given quantities of both, that's a limiting reactant. And before you do anything else, you need to determine what the limiting reactant is, right? So I've got to do stoichiometry with both of these reactants to figure out how much product they can each make. And remember, the one that makes the least amount of this NH3 is going to be your limiting reactant. And it's the quantity made by the limiting reactant that's the theoretical yield, which is what you're looking for. Anyway, give it a shot on your own, then come back. All right. I'm going to do nitrogen first. So, and remember that decimal is telling you that has 3 sig figs, right? So that'll be important eventually. So 100 grams of nitrogen. I know my first step is always to convert the material I'm starting with to moles. Since I have grams, I've got to use molar mass on the periodic table. Make sure you carry plenty of digits in your molar mass. The molar mass of N2, nitrogen's a diatomic, so it's 2 nitrogen atoms. All right, so now that would give me moles of nitrogen. Now I'm going to use mole ratio to get to the product. Remember, I'm trying to figure out which of these reactants makes the least amount of product. So I'm going to put moles of N2 in the denominator so it cancels. And I know from the balanced reaction there's a 1 in front of that. And I'm trying to get to the product, which is NH3, and there's a 2 in the balanced reaction with that. All right, so if I were to stop now, I can stop now. Yeah, I'll stop now. 2 moles of NH3. Now we got to figure out, and you could take it to grams if you want to, but it's a little bit less work to stop at moles. Now I'm going to do the same thing for hydrogen, and I'm going to figure out how much NH3 that 50 grams of hydrogen can make. So hydrogen's another diatomic, so be careful. Its molar mass, need 2 hydrogen atoms. And okay, so once I get it into moles of hydrogen, I'm going to use a mole ratio to convert that to moles of NH3. Now hydrogen, hydrogen has a coefficient of 3 in the balance reaction. And of course NH3 has coefficient of 2. All right, so now I am going to calculate both of these and determine what my limiting reactant is. So 100 divided by 28.02 times 2. So that tells me 100 grams of nitrogen can potentially make 7 point. I'm going to carry extra digits for now because I can't remember, but I think I have to go to grams. All right, so that can make that around 7 moles of ammonia. Let's see how much the 50 grams of hydrogen can make. Ooh, that can make 16. And again, I'm just putting extra digits for now, okay? All right, so what is my limiting reactant? It's the one that makes the least amount of product. So that's not my limiting reactant. That's my theoretical yield. My limiting reactant, you have to go all the way back to where you started. This is my limiting reactant. And so that means from here on in, don't use anything to do with the excess reactant. Okay, don't do anything with it. So now if the problem had asked for how many moles of NH3 can be made, that would be your answer, but typically it'll ask for grams. And so once you have the limiting reactant, you would go ahead and do one more calculation to get grams. And so the molar mass of ammonia is 17.04 grams per mole. And so now, if we multiply those out, they will give us the grams, the theoretical mass that can be made. So 7.1378 times 17.04. Right, so the theoretical yield, and now I'm going to round it to 3 sig figs because that's what I started with. Theoretical yield is 122 grams of NH3 can be made. That's the theoretical yield. Remember, the theoretical yield is the amount that can be made by the limiting reactant. All right. We've talked about theoretical yield quite a bit, but it turns out there are 3 different types of yield. There is theoretical yield, which is the calculated amount that the limiting reactant can make. There is actual yield, which is what the chemist actually makes in the lab. Okay, so the actual yield, theoretical yield, is that if everything was perfect and 100% of the reactant converted. That never happens, okay? You're usually lucky as a chemist when you get at least 70% yield. So the actual yield is going to depend on the conditions of the reaction, equilibrium, all sorts of things. And then, of course, there's percent yield. So you need to know the difference between all of them. Actual yield must be given to you, okay? Because it's going to depend on the equipment you have, the chemist, how long you let it go, all sorts of things. So that has to be given to you in a problem. Now, of course, chemists always want to know what the actual yield is compared to the theoretical yield, right? What ratio of the product did they get from what they could have gotten? And that's percent yield. So this is a formula you need to know, okay? Percent yield is simply the ratio that the chemist gets, the actual yield over the theoretical yield, the calculated amount that could have been made, times 100. And so that's a real common thing to have to calculate. So here's another example for you to try. Let's see, 14.4 grams. I like to write the given information under the chemical reaction. It just kind of helps me visualize what I'm trying to do. 14.4 grams of aluminum. When a reaction says excess, that means it's not a limiting reactant. They're telling you what the limiting reactant is. They're telling you that aluminum is the one that counts. It's a limiting reactant. It's all you need to do a calculation with. So you can just kind of ignore the other one. All right, so the first thing you need to do is to calculate the theoretical yield. Now you have two products, so which product are you going to go to? The one they ask you about, okay? They're asking you about hydrogen. So again, you're going to ignore the other one. So you're trying to find out how much hydrogen you can get. So what is the theoretical yield of the hydrogen? Once you calculate that, theoretical yield is always what you get from stoichiometry. You want to calculate percent yield. So what is this they gave you here? That's the actual yield, right? Anytime they give you an amount of a product that's collected, that is the actual yield. And then remember your percent yield formula, right? It's going to be the actual yield, which is 1.05 grams, divided by the theoretical yield that you calculate, right, times 100. So go ahead and give that a shot, and then come back here and I'll work it out for you. Start with a given, of course, always. 14.4 grams of aluminum. Now remember, the process that we're almost always going to go through, right, is grams of whatever the given information is. First thing you have to do is go to moles of that substance. Once you're in moles of that substance, you can use mole ratio to go to moles of any other substance in the chemical reaction. And then finally grams of that. So almost always, it's going to be a three-step calculation. So we need the molar mass of aluminum to convert to moles of aluminum. Okay. Now that I'm in moles of aluminum, I can use mole ratio to get to the substance the problem is asking about, and the problem is asking about hydrogen. I'm going to go to the balanced reaction to get the coefficients for the mole ratio. So there's a 2 in front of the aluminum and a 3 in front of the hydrogen. If I were to stop here, my units would be moles of hydrogen. The problem is asking for grams. Well, I need to find grams, theoretical yield. And so I need the molar mass of hydrogen, which is diatomic. So it's 2 hydrogen atoms. All right, so all of that's going to give me the theoretical yield for hydrogen. That is, how much hydrogen can be made if all of the given aluminum is reacted. So I'm going to go ahead and plug that into my calculator real quick. And I get that I can make 1.62 grams of hydrogen. That is my theoretical yield. Okay, now I'm going to calculate percent yield. So the percent yield is the actual, which was given, 1.05 grams divided by theoretical, 1.62 grams, times 100. And let me punch that in real quick. And I get that the yield is 64.8%. That's it. Now we're going to finish. The last topic in this lecture is how to calculate how much excess reactant is left over. That happens to be a type of problem that I typically give as a bonus question on my exam. It's a little bit higher level, which is why I count it as bonus. But here are the basic steps involved. you always have to find limiting reactant. That's the first thing you do to find quantities of anything, theoretical yield, but also how much excess reactant. Once you know what the limiting reactant is, you will use that and stoichiometry to figure out how much excess reactant actually reacted or how much was used up, right? So you're just going to use the mole ratio between the limiting reactant and the excess reactant to calculate how much of this excess reactant did I actually use in the reaction. Once you have that, how much was actually used, you can subtract how much was used from the initial amount of excess reactant. So let's say the problem told you that you had started with 25 grams of some excess reactant A, and then you did a calculation with your limiting reactant and you found out that you only used 20 grams or only needed 20 grams of A. That would mean that your excess reactant that was left over would be the difference between those. All right, so here's a sample problem for you. It kind of walks you through it. And so if you're in my class and you want to get a bonus on the next exam, you can become an expert at this, okay? So here's a typical limiting reactant problem. You know it's a limiting reactant problem because it gives you quantities of both reactants. So I'm going to figure out how much each of the given amounts of reactants, how much product they could theoretically make. The one that makes the least, okay, so this is the theoretical yield, right? The one that makes the least is the limiting reactant. So iron 3 chloride was the limiting reactant, which means hydrogen sulfide was the excess reactant. All right, so now how much of this excess reactant actually got reacted? To figure that out, everything depends on the limiting reactant, right? So again, you're going to start with the limiting reactant now that you know which one it is, and you are going to use the mole ratio now between the limiting reactant and the excess reactant because you're trying to figure out how much excess reactant actually reacted. So that will give you how much of the excess reactant reacted. You know how much you started with, right? You started with 52 grams of that excess reactant. So you subtract what you just calculated here. Ooh, where did I get 27.4? I changed it. That should be 28.4. But anyway, so you subtract the amount that actually reacted from the amount you started with, and that gives you the excess reactant that's left over or unreacted. That is it for this PowerPoint.